Okay, guys, this week we've been studying atoms. We're going to look at symbols that we learned in Build an Atom. We're going to go on to 8-man and our atomic models. So let's get started. Whenever you're looking at a symbol, in the upper left is your mass number. Your mass number is your protons plus your neutrons added together. On the lower left, you have the atomic number, which is just the protons, and it identifies the atom. You change the symbol, you change the atomic number. You change the atomic number, you change the symbol. The charge is a relationship between the protons minus the number of electrons, because electrons are negative. Now, in other classes, more advanced classes, you might see these symbols A and Z. It's a little weird that mass number is A and atomic number is Z. It turns out they're from German background words. Okay, so let's get started interpreting our symbols. So we are looking for the protons, electrons, and neutrons, our three subatomic particles. The protons is the best place to start because that's the atomic number. There's no charge here, 0, if there's nothing there. That means protons and electrons are equal. To find the neutrons, we use man. Our mass number minus atomic number will equal the neutrons. So I'm going to subtract, and I get 18. Okay, we're going to keep going. You can see the symbol hasn't changed. That means the protons haven't changed. And its charge is still 0, so the electrons are still 19. They're equal to the protons. Let's use the man, subtract, and this time we get 20. We're going to continue. Again, its charge is still 0. It's still K. It's still 19 protons and electrons. We're going to use man, mass minus atomic number, to get our neutrons. And now it's 21. And last, and again, hopefully you're seeing patterns here. And if it goes too fast, make sure you're or pausing the video or rewatching as needed. K is 19. Charge is still 0, so protons and electrons are equal. And use our man to get the neutrons, and this time we get 23. Okay, what I would like you to notice is that all of these are the same symbol, same protons, but different neutrons. There's a special word for this. It's called an isotope. So you want to put this in your written notebook. You might want to pause and go get that, or your index card system. Isotopes are the same element. It has to be the same element, and therefore it has the same protons or atomic number. And what's different about them, in fact, the main thing that's different about them is the mass. And why is the mass different? Because the the neutrons are different. Okay, protons stay the same, the neutrons change. That changes the mass. Isotopes. Good vocabulary word. Let's take another look. And this time, we're going to have some charges involved. Again, upper left is always the mass number, which is the protons plus neutrons. The charge is protons minus electrons, and the atomic number is the protons. So let's do our protons, electrons, and neutrons. That's our three subatomic particles. Lower numbers are protons, but this time it's not a neutral atom. And this time there is a +1 charge. So now let's go ahead and do the work. Protons are 19. We don't know the electrons. I'll leave it E or X. But we know the charge has to add up to +1. So what's E have to be? 18. +1 implies that you lost one negative thing. 18. And the neutrons, again, back to man. Don't forget, minusing for man. And we get 18. Okay, now let's take a look at another ion. Whenever the charge is not 0, we call these things ions. Protons, 12. The electrons are not 12. This time, they've lost 2 negatives. Or if you like looking at the math, 12 minus electrons has to equal +2. So 10. Notice it started off with 12, but when it was neutral, it lost 2. or you can do the math. Man to get our neutrons, and subtract, and we get 13. These would not be isotopes. They have different symbols, different protons. Okay, let's keep going with our pen, our protons, electrons, and neutrons. Protons, electrons, not going to be 6. This time it's gained 4 negatives. Or we can look at the math. 6 minus the electrons equals negative 4. So if you solve for E, this has to be 10. 6 minus 10 gives us negative 4. So you can see how it's gained 4 negatives or 4 electrons. And we do man to get our neutrons. Last one. Protons. Notice we always start there. Okay, not neutral. Protons minus the electrons equals negative 2. So negative means it's gained. How many? 2. That's 10. 8 minus 10 is negative 2. Do our man. Subtract to get our neutrons. None of these are isotopes because they're not the same element. That's the main and first requirement for an isotope. These are all different ions. So let's take a look at man and ape in another format. We know ape, atomic number, protons, and electrons are all equal in a neutral atom. And man, we've been using mass number minus atomic number equals neutrons. Let's take a look. When they give it to you in this form, this is always going to be the mass, which means they don't give you the atomic number. You have to look it up. We use our periodic table. Atomic number is in the lower left. It's 11. Okay, so there we go. Atomic number is 11, so that means the protons are 11. There's no charge here, so electrons are also 11. Now, electron configuration is something else you can get from the periodic table. If you zoom in, we have 2, 8, 1. It goes right under the atomic number. Notice 2, 8, and 1 add up to 11. So it's not 2 minus 8 minus 1. Those are dashes. And they tell you how the electrons are configured or organized in the shells. And we'll look at that in a minute. Last, we do our man. Atomic number is 11. Bring that over. Mass number minus atomic number equals our neutrons. We're going to use all of this information to do our Bohr diagram. Niels Bohr is one of our models, the planetary model, the solar system model, where the protons go in the center and the neutrons also go in the center, called the nucleus. And then the electrons go in organized shells or layers. 2 in the first, 8 in the second, 1, 2, 3, 4, 5, 6, 7, 8, and 1 in the last. That's a Bohr diagram. Now, a Lewis diagram is much easier. You just put the symbol, Na, and you only care about the last electron. This is called the valence electron. And the valence electron, it turns out there's only one of them. We use it represented by a dot. Does all the reacting or reactivity for an element. We'll take another look. Sodium 23, sodium 22. These would be isotopes. Mass number is 22 this time. Atomic number for sodium is still 11. That doesn't change. Protons are still 11. And there's no charge, so electrons are also 11. The electron configuration hasn't changed to 8, 1. The atomic number is 11, and we use our man and subtract, and we get 11 neutrons. Again, last time for Bohr model. Make sure you're really getting a last look here. 11 protons, this time 11 neutrons. And the electrons are 2, 8, 5, 6, 7, 8, 1. The Lewis diagram still cares only about that last one, 1. Notice these isotopes, the masses are different, right? And the neutrons are different. Okay. So a last look at the models over time. We start with the solid sphere model back in early 1800s with John Dalton. Notice it has no parts. And then we start discovering subatomic particles. Thomson discovers this electron. Looks like the chocolate chip cookie. They call it the plum pudding model, where the electrons are the little negative pieces of plum and the positive goo is the pudding. Okay, Rutherford in the early 1900s made a big leap. We have a nucleus now, a positive nucleus, which in actuality is not represented. It will be much smaller. And electrons are outside the nucleus whizzing around in lots of empty space. Niels Bohr refined that. He put the electrons in organized orbitals, or we would say energy levels. The nucleus is still positive. And last, even though this looks simple, this is our current model. We still have that positive nucleus with protons and neutrons, but now we understand that electrons aren't in discrete energy levels. They're in energy areas we call orbitals, or areas of high probability. Electrons are very unpredictable. Okay, we're going to learn more about atoms as we keep going in the unit, and that's all.